This is part 5, building pressurization for acceptable indoor air quality. We're going to start off with standard 62 and because we're talking about air quality here. And what does standard 62 say about pressurization? It talks about building exfiltration. And it says ventilation systems shall be designed such that the total building outdoor air intake equals or exceeds the total building exhaust under all load and dynamic reset conditions. So again, it's an operational standard, makes 62 an operational standard. And in the informative note, I think this kind of sums it up. Net positive mechanical intake airflow for the building as a whole reduces infiltration of untreated outdoor air. Now, in reality, there's an exception for standard 62. They seem to be more focused on indoor air quality problems resulting from moisture, mold, and fungal growth. But in reality, we have issues with untreated outdoor air even when there's not moisture in the outdoor air. So when we take a look at this, and Standard 62 recognizes it, negative pressure and IAQ are really, it's really an IAQ nightmare, particularly in humid climates, but it's not just in humid climates, it's everywhere. Okay, and the reason for that is, let's say that we're cooling. What we're doing when we're cooling, if we're negative, is we're basically transporting three things. We're transporting untreated outdoor air, unfiltered, in terms of dirt, dust, pollen, whatever's in the outdoor air into this space. Also, we have perimeter temperature control problems from heat. And in moist climates, we have that additional problem of moisture in the outdoor air being transported across the building envelope or into the building without ever crossing over a coil. And that's why it's so serious from an IAQ perspective. I put this together in the probably mid-90s. I was very fortunate. My good friend in high school and roommate in college ended up being a professor of meteorology at Penn State. And, in the 90s, you couldn't just go grab data like you could grab it today off the internet. And he gave me 10 years of hourly wet bulb and dry bulb temperatures from 700 weather stations. And it was really good information for me. And I took some of that data and I created this map because I was looking at when was the dew point greater than 65 degrees. And the reason I chose 65 degrees was that if you have an envelope temperature or wall temperature interior of 74 degrees, 65 degrees equated to relative humidity of 70% or higher. And at the time, that's what I was doing a lot of mold research, and I was like, well, I found that the molds that I was concerned with, most of them, not all of them, really thrived in relative humidities of 70% RH or greater. So that's where I came up with that number. And maybe, I look at it today and say, gee, maybe I should have done this with 60 degrees instead of 65 degrees, but it really doesn't change much of my argument, okay? And when you look at this, what you see here is the folks in Florida and Texas, and even us in the Carolinas, we get it over half of the year, these conditions of high dew point outdoor air exist. So we are very cognizant of mold problems, but you know what? It's not just the southern United States, okay? It goes all the way up. And it doesn't matter if you're in Maine, it doesn't matter if you're in Minnesota. I don't show it in Canada, but parts of Canada, it's really a problem, as well as Southern California and the Southwest there. And honestly, when I look at this, and you'll understand what I'm saying in a few minutes, it's actually more widespread than what I show in this. Okay, so the first thing I wanted to do is I want to get an understanding of what is the problem. You're out talking to people in the 90s, there wasn't a lot of this information available. And so it's like, what's causing mold in buildings? Is it leaks? Is it, vapor pressure gradients? Is it moisture from building pressurization? It was really hard to tell. It ends up it's all of them, okay? But what ends up happening when you look at this is I said, hey, I want to look at when the dew point is greater than 65 degrees, how much water am I transporting? And so I said, well, if I ran a building 1,000 CFM negative when the dew point was over 65 degrees, how much water did I transport? And I found like in Miami, it was almost 1,000 gallons per year. And tapered off, of course, as I went north. And then a few years went by, and I was like, it's really not how much water did I transport in a year. It's how much water do I transport a day when these conditions are are favorable for mold growth because mold can take only a few hours to grow. It doesn't take days or weeks necessarily to grow. So I redid the graphs and then I looked at it and I said, well, this is obvious to me now, but it doesn't matter where you are in the country. When a dew point's over 60 or 65 degrees and your building's negative, you have the potential for mold to grow in the building envelope, all right, on surfaces, and you're going to have the potential for humidity and temperature control problems in the space. So it's a big deal. Then I run into people that are like, well, it doesn't matter if we're economizing. It's like, well, yeah, it does. The difference is you're not bringing in moisture, but you still have untreated outdoor air, and you still have temperature problems and dirt, dust, and whatever's in the outdoor air. And the same is true in heating. Heating can get a little complicated in cold climates where the humidity inside the building becomes a problem, and positively pressurized spaces actually create some other sets of problems. But from an IAQ perspective, and particularly from a perspective of untreated outdoor air, negative's a problem, and it's not just a problem when in the hot, humid climates. All right, so the thing is, does building pressure really matter for the average building? And of course, the answer is absolutely, all right? But when we're talking about building pressure, we're really not pressurizing a building. You don't pressurize a building, you pressurize a compressed air tank. What you're doing is you're using your mechanical system, and then, there's a pressurization airflow created, and that pressurization airflow creates a measurable pressure drop. And that's why so many people gravitate and call it building pressure and try to actually control the measured pressure drop associated with the pressurization flow. But that's not really what you're trying to do, okay? You're really trying to use your mechanical system. And in fact, the only way you can pressurize a building is with your mechanical system, all right? So what is it all about? Well, it's all about these different potential mechanical paths, right? We have the outdoor air path that we're going to be using for sure for dilution ventilation, but we could be using for free cooling. And we have our relief air path that's going to relieve excess outdoor air. And we also have our exhaust path. And, intuitively, these are the things that you want to measure. Now, it ends up on a lot of your systems, these are the only paths you could measure. But fortunately, also, we have an additional way we can look at this on recirculating air systems because there's another place we can look at. So if we're positive, we're positive. We have more outside air than the combined relief exhaust. We're positive, we're negative, we're negative. Like I said, when we get into recirculating air systems, we have some other options. And there's two reasons I want to point this out. It's one, I want you to understand that when we get talk about doing this, these other options are better places typically to measure for more accurate flows, but also to let you know that if you aren't understanding that this affects building pressurization, anything you do that affects supply return airflow differentials is going to affect the pressurization of the building. And so if you do sloppy fan tracking or ride fan curves and things like that, you have a potential for some real building pressure problems. So let's take a look at this. I want to look at this one first point here. If I look at this point, what I see is I can make an equation that says if the recirculation air plus the outside air basically is equal to the supply air, those rates. The recirculation air plus the outside air equals the supply air flow. Okay, that's an equation. Now I want to look at this other point. It's the same, basic system here. And same kind of thing. It's going to be the recirculated air plus the relief air now equals the return air. So I have two equations, right? So if I subtract these two equations, I still have an equation. And what I find is outdoor air minus relief air, what I'm really interested in, is also mathematically equal to supply air minus return air. And so it's going to give us other alternatives for measurement on recirculating systems, but I also want to point out to you that anything you do that results in what I would call sloppy flow tracking is going to result in sloppy pressure control. And that's the big thing I want to point out. That's the end of part 5. In part 6, we're actually going to integrate dilution, ventilation, and pressurization control into a single control strategy. So I'll see you in part 6.